In this video, we're going to learn about inscribed angles. An inscribed angle is an angle that is composed of 3 points on a circle, like this angle in green here. It's an inscribed angle because this point, and that point are all on the circle. So let's go ahead and label that angle, and we call it an inscribed angle. In contrast, this angle here in red has only 2 of the points on the circle, and the vertex is at the center of the circle. And this angle is called a central angle. And that's intuitive because the vertex is at the center of the circle. Now there's a cool relationship between inscribed angles and central angles. The measure of an inscribed angle is related to the measure of the central angle, which intercepts the same arc. Actually, it's equal to a half of the central angle, which intercepts the same arc on the circle. So in this diagram here, because these 2 angles intercept the same arc on the circle right here, the measure of this inscribed angle is half the measure of the central angle. So let's go ahead and use this fact to solve for each of the missing variables in the diagrams below. First of all, we've got this circle here, we've got an inscribed angle of x and a central angle of 30 degrees. So we'll just go ahead and apply this formula. The inscribed angle, x, is equal to a half of the central angle, so a half of 30. And a half of 30 is just 15. So there we go, x is 15. We can do a similar thing for this next problem, which has a central angle y and an inscribed angle of 20 degrees. Let's just go ahead and use this formula to set up an equation. So inscribed angle is 20, and that's equal to half of the central angle. So 20 equals y over 2. So to solve for y, we can just go ahead and multiply both sides by 2 and get 40 equals y. So there we go, it's solved. Okay, this next problem is a bit harder. We've got a triangle inscribed inside of the circle. We know 2 angles of the triangle, 60 and 40 degrees, and we want to find the length of this arc here, z. So where do we even begin? Well, why don't we work backwards? We know that z degrees of arc corresponds to a central angle of z. So why don't we go ahead and construct a central angle here? So this central angle here, that'll also be z degrees. Okay, and then is there any way that we can find that central angle? If we knew an inscribed angle which intercepts the same arc, then we could just use this formula, inscribed angle equals central angle over 2. So is there any inscribed angle which intercepts this arc? Well, yeah, it's right over here. This inscribed angle right here. Unfortunately, we don't know the measure of that inscribed angle, but can we figure it out? This is part of a triangle, and the angles of a triangle have to add to 180 degrees, and we know 2 of the angles, so to get this measure of the inscribed angle, we can just start out with 180 degrees and then subtract off the other 2 angles, 180 minus 60 degrees, and then minus 40 degrees, that other angle. And 180 degrees minus 60 degrees, that's 120 degrees, and then subtract 40 degrees, and we get 80 degrees. So the inscribed angle is 80 degrees, and finally we can go ahead and set up an equation here. So 80 is equal to the central angle, which is z, over 2. And we can solve that by just multiplying both sides by 2 like we did in the previous example. So multiply both sides by 2, 80 times 2 is 160. So 160 is what z is equal to. Next up, we want to prove that if 2 inscribed angles x and y subtend the same arc, then they are congruent. So here we've got a diagram. We've got a circle with 2 inscribed angles x and y, and they both subtend the same arc, which is right over here. Let's just color that in a little bit. Okay, so they both subtend the same arc, and we want to prove that they are congruent, which really means we just need to prove that they have the same measure. Now, the fact that an inscribed angle is half the measure of a central angle is going to come in very useful here. Let's go ahead and construct a central angle which subtends the same arc. So we'll have it going from the center to each endpoint of the arc, and then we'll call that z. Now, since the measure of an inscribed angle is half the measure of a central angle which subtends the same arc, we have that, for example, measure of angle x is equal to half the measure of angle z. So measure of angle z over 2. Likewise, it's the same idea for the inscribed angle y. Measure of angle y is also equal to half the measure of the central angle z, which subtends the same arc. And now by the transitive property, we can say that since the measure of angle x and the measure of angle y are equal to the same thing, they have to be equal to each other. So measure of angle x equals measure of angle y. And because of that, we have that angle x is congruent to angle y. So there we go. We're done. Alright, so we've been using the fact that the measure of an inscribed angle is equal to half the measure of a central angle which subtends the same arc. But why is this even true in the first place? That's what we're going to learn in this question. We need to prove that if a central angle of measure c degrees and an inscribed angle of measure x degrees both subtend the same arc on a circle, then x equals c over 2. Now the general proof is a little lengthier, so here we're just going to assume the special case where one chord is a diameter. That way we can get through the proof reasonably quickly. Alright, so we've got a diagram here. We've got our central angle c degrees, we've got our inscribed angle x degrees, and we are assuming that one chord of this inscribed angle is a diameter. And that's this chord right over here, runs through the center of the circle. Now we want to show that x equals c over 2. So how are we going to do that? Well, a good way to start this off is to just begin by filling in all the information we know. Are there any other angles that we can solve for? Well, hey, this angle c degrees is supplementary to this angle here. They add up to 180 degrees. So that means this angle here has to be 180 minus c degrees. And is there anything else that we know? Well, since this is a center of the circle, we've got some radii here. There's a radius, there's a radius, and there's a radius. And the radii all have to be the same length. So in particular, this triangle here needs to be an isosceles triangle because two of its legs are radii. So two of its legs have to have the same length. And we know that in isosceles triangles, the base angles need to have the same measure. This is one of the base angles, x degrees. This is the other base angles. That also needs to be x degrees. So now we've got all the angles of this triangle expressed in terms of the variables x and c, and we can say that they all have to add up to 180 degrees, because that's how many degrees are in a triangle. And that gives us a nice equation that relates x and c. So x plus the third angle, 180 minus c, is equal to 180. Let's go ahead and solve for x in this equation. First of all, we'll just simplify. So group up this x plus x into 2x. And then we have just plus 180 and minus c. And that's equal to 180. Now we've got 180 on both sides, so we can subtract 180 from both sides and cancel both of these out. And we just have then 2x minus c equals 0. Now to get x alone, we can add c to both sides. So we'll have 2x equals c. And then just divide both sides by 2. That'll cancel out the 2 that's on the x. And we end up with x equals c over 2. So there we go. We've got it. That's what we wanted to prove. The measure of the inscribed angle, x, is equal to half the measure of the central angle. So now we know how to work with inscribed angles in circles. And in the future, we'll continue to learn about more geometric constructions in the context of circles.